With each enamoring picture caught by the James Webb Space Telescope, thoughts emerge from different corners of the universe, including planets within our own solar system. A year earlier, we contemplated our first brief glimpses at images showing the Carina Nebula, the Stefan's Quintet, and strikingly, the mesmerizing Deep Field image. This specific picture clearly portrays various galaxies stretching into the vast expanse of the universe, fulfilling the presumption made by the James Webb Space Telescope. The telescope hasn't stopped at merely revealing beauty. It has recently uncovered objects that challenge established cosmological theories. These astonishing revelations are now marked as universe breakers by cosmologists, bewildering the scientific community with their capacity to defy existing concepts. The reasons for these discoveries remain shrouded in mystery, throwing our hypotheses and speculations into confusion. So, what's the latest scoop from the James Webb Telescope? What unprecedented new discoveries has it revealed that were previously unknown to us? Join us as we delve into how the James Webb Telescope has introduced evidence suggesting the existence of another universe, testing the conventional understanding of the Big Bang. Our universe, as we've long perceived, emerged from a hot, dense state through a theory known as the Hot Big Bang. This thought, a significant scientific achievement over the last century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background, CMB, a remnant from the early hot and thick state. Over time, the Big Bang theory has remained the prevailing explanation for our universe's origins. However, new and critical observations have prompted cosmologists and astrophysicists to address both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, emphasizing the enduring nature of the theory of the universe's origin. According to the general viewpoint, the depiction of the universe's beginnings involves a smaller, denser universe in the distant past. The presence of radiation, like photons, indicates that the universe was hotter at its inception and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels reach a point where a singularity could form, causing the normal laws of physics to break down at around /10⁻⁻43 seconds. During this brief period, tiny distances, short durations, and high energy scales challenge our comprehension, rewinding the cosmic clock to a speculative 0 point. If the universe began hot and dense, it then expanded and cooled, producing vast quantities of particles and antiparticles, with excess particles annihilated by radiation as temperatures dropped. The breakdown of the electroweak and Higgs symmetries led to the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles known as quarks and gluons. The combination of protons and neutrons resulted in the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions experienced expansion due to radiation pressure, followed by gravitational collapse, leading to the development of large-scale structures around 380,000 years after the Big Bang. The universe cooled sufficiently for stable neutral particles to form, marking a critical moment when photons decoupled, and their frequencies stretched as the universe evolved. The discovery of the cosmic microwave background decades ago solidified the Big Bang theory as the most supported explanation for the universe's creation. While most cosmologists and astrophysicists embrace the Big Bang theory, ardent supporters of the steady-state hypothesis like Fred Hoyle continue to defend increasingly improbable claims, only to face rout in the face of overwhelming evidence. The proof presented was conclusive. It wasn't merely blurring starlight or reflected heat from dust. The grandiose glow displayed an astonishing consistency in all directions, resembling an ideal black body yet having no association with known objects in the universe. Despite this, Hoyle and his adherents continued to obstruct scientific advancement by supporting tentatively misguided theories. Meanwhile, the fields of space science and cosmology experienced exceptional growth from the 1960s through the 2000s, with cosmology witnessing particularly striking advancements. We mapped the vast universe and described its structure on a grand scale, exploring the evolution, formation, and dynamic interactions of galaxies and their cosmic populations. However, despite these advances, we encountered inconsistencies that resisted explanation within the framework of the Big Bang theory. observations revealed disparities that challenged the current validity of the theory regarding how things came to be. Most notably, the absence of exotic particles predicted by the theory, such as magnetic monopoles or particles from grand unification, leaves the universe we see today seemingly requiring forces beyond our current understanding. Yet, these remain elusive. At its origin, the universe required an exact rate of expansion to balance the total energy density, an achievement that the theory of the universe's origin struggles to justify. Achieving neither firm balance nor adequate time for energy exchange across different regions of space. Given the universe's boundlessness and its expansion over time, these anomalies pose significant challenges for cosmology and the scientific community. In summary, when theories fail to account for observed anomalies, two approaches emerge: refine existing hypotheses or consider alternative explanations. The theory of inflation arose as the most promising hypothetical framework for extending the Big Bang perspective. Inflation proposes a period of rapid expansion, smoothing out the universe and enriching it with uniform properties. It addresses the horizon problem and predicts the formation of quantum fluctuations, manifesting as density and temperature variations. Prominently, inflation's predictions align with observed patterns and variations, supporting its legitimacy. While alternative theories exist, inflation's scientific strength remains unmatched. Nonetheless, despite past commitments to general relativity and singularities, Roger Penrose's work, including his collaboration with Stephen Hawking, failed to match the development of inflation in explaining the universe's earliest moments. Recently, there has been deliberate work to undermine the credibility of inflation theory, advocating instead for conformal cyclic cosmology, which is intrinsically flawed from a scientific perspective. The key distinction lies in their predictions. Conformal cyclic cosmology asserts that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflation theory maintains that the point where inflation ends and a hot Big Bang begins should be causally detached from any pre-Big Bang region. Every aspect of our universe exhibits remarkable characteristics, suggesting that we should rely on the universe itself to reveal what is true, rather than merely depending on theory, overlooking foundational shocks. Cosmologists quickly recognized peculiarities in the images transmitted by the James Webb Space Telescope since 2022. These discoveries may necessitate a reassessment of key elements of the universe's origins and evolution. One significant revelation made by the Webb telescope was the presence of mature galaxies much earlier than expected by the standard model of cosmology. This inconsistency challenges the established timeline following the Big Bang, where stars and black holes formed first, followed by the development of galaxies. Such revelations disrupt our understanding, akin to encountering grandparents depicted as children in a narrative. Additionally, recent evidence has unveiled peculiarities within fundamental hypotheses about the universe, such as the ongoing discrepancy in determining the Hubble constant, which persists despite improvements in data precision and collection methods. Furthermore, new data from the Webb telescope exacerbates existing challenges to the current cosmological model. These issues highlight flaws within the model itself, prompting inquiries among cosmologists and physicists. While the model has undergone modifications over the past 50 years to align with emerging data, some argue that these changes have been overly convenient. Thus, there is growing recognition that a shift in perspective might be essential to reshape our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe during the 1920s. Subsequent revelations, such as the cosmic microwave background radiation in 1964, confirmed the theory of the universe's origin, portraying the early universe as a hot, dense soup of subatomic particles continuously cooling over time. However, achieving the current level of accuracy in cosmological understanding has necessitated hypothetical extrapolation beyond observational data. The theory of inflation, proposed in 1981, was introduced to resolve abnormalities in previous Big Bang models, further emphasizing the unique nature of cosmological theory. According to this hypothesis, the early universe underwent rapid, exceptional expansion for a brief period following the Big Bang. While certain issues are resolved by this concept, new challenges arise, especially considering the prevailing belief in the existence of one universe, potentially countless others beyond our observational reach. Certain discernible oddities, like hypersingularities within black holes, find support through indirect evidence. However, the remarkable discoveries of the Webb Space Telescope regarding the development of galaxies and the ongoing issue with the Hubble constant raise concerns that we may be approaching a tipping point where a significant upgrade of our current cosmological model becomes essential. This could necessitate a reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, grapples with fundamental questions about the universe, its origins, and the role of observers within it. The exploration of consciousness and quantum physics delves into similar subjects, investigating the intersection of theory and reality while challenging major assumptions that underpin our understanding. Testing assumptions, such as the constancy of physical laws over time, has been proposed by researchers like Roberto Mangabeira-Unger and physicist Lee Smolin, who suggest that physical laws may evolve and change. Testing traditional paradigms, physicist John Wheeler even proposes that every observation can impact the universe's past and future, significantly rethinking scientific practices. It is essential to examine these foundational assumptions, given the influence of theoretical suppositions on data collection. History has shown that disruptions in scientific thought, such as the shift from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to significant changes in societal perspectives. A similar effect on our understanding may be anticipated from any forthcoming scientific upheaval in cosmology. Philosopher Robert C. Coons argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers to a question. The ongoing debate centers around whether theory is necessary to address cosmological fundamentals. If modifying existing models proves inadequate, a complete overhaul of our comprehension of the universe may become necessary. Recent advancements in observational technology have transformed how we interpret the universe. The James Webb Space Telescope, with its cutting-edge instruments, allows astronomers to peer farther back in time than ever before, capturing light from the early universe that has traveled billions of years to reach us. This capability has transformed our understanding of cosmic history, revealing patterns and anomalies that challenge long-held beliefs. One of the most significant implications of Webb's revelations is the potential for rethinking the timeline of cosmic evolution. For instance, the discovery of mature galaxies only a few hundred million years after the Big Bang raises questions about the speed and nature of galaxy formation. This observation suggests that the cycles governing star and galaxy development may have been more complex and efficient than previously understood. The ramifications of this challenge existing assumptions about the ongoing development of large structures imply that large-scale star formation might have occurred much earlier than current models anticipate. Additionally, the identification of exceptional patterns in the cosmic microwave background radiation, combined with data from Webb, suggests that our universe may be more homogeneous and isotropic than the Big Bang model can fully explain. This has sparked discussions about the possibility of a multiverse, where our universe is merely one of many, each with its unique properties. Such a perspective wouldn't just redefine how we understand physical laws, but also expand the limits of scientific inquiry, as we may not be able to directly observe other universes. As cosmologists continue to explore the data from Webb, the potential for discovering exoplanets and habitable zones around distant stars has reignited interest in astrobiology. The investigation of the conditions on these exoplanets could yield insights into the chemical signatures of life beyond Earth. Researchers are especially eager to identify biomarkers, substances that could indicate the presence of biological processes. This search could ultimately lead to profound philosophical questions about our place in the universe and whether we are alone in the vastness of space. Recent revelations from Webb have also prompted a reconsideration of dark matter and dark energy, two of the universe's most perplexing components. The inconsistencies observed in galaxy rotation curves and the distribution of large structures may suggest new interactions or particles that diverge from existing theoretical models. The ongoing investigations by the James Webb Space Telescope, JWST, continue to redefine our understanding of the cosmos. As astronomers analyze the telescope's data, new hypotheses emerge, challenging the foundational concepts that have long shaped cosmological discourse. One of the most profound areas of inquiry is the nature of cosmic inflation itself. While traditional models suggest a rapid expansion following the Big Bang, recent findings imply that this process may have been more intricate than previously thought, possibly influenced by unknown variables. Moreover, the JWST's advanced capabilities allow scientists to probe deeper into the formation and evolution of celestial bodies. This includes studying the atmospheres of exoplanets, which could reveal insights into their potential habitability. The discovery of chemical signatures indicative of life-supporting environments on these distant worlds could transform our understanding of life's prevalence in the universe. Another significant aspect of JWST's findings relates to the distribution of galaxies. Observations suggest a greater variety in galaxy morphology than current models predict, raising questions about the mechanisms driving galaxy formation and interaction. This could lead to revisions in the timeline of galactic evolution, indicating that complex structures formed much earlier in the universe's history than once believed. The interplay between dark matter and dark energy also remains a focal point of research. As JWST captures detailed images of galaxy clusters, scientists are reevaluating how these invisible components influence cosmic structure. The potential discovery of new particles or forces could bridge existing gaps in our understanding, prompting a reevaluation of fundamental physics. Additionally, the JWST's findings encourage interdisciplinary collaboration, merging insights from cosmology, astrophysics, and even philosophy. As we grapple with questions about existence, the nature of reality, and our role within it, the telescope serves as a powerful tool for exploration. Its ongoing revelations are likely to inspire a new generation of scientists, thinkers, and dreamers, igniting curiosity about the universe's profound mysteries. As we delve deeper into this cosmic journey, the potential for paradigm shifts remains vast. Each new discovery from the JWST may well alter our trajectory in the quest for knowledge, pushing the boundaries of what we consider possible.